You know that feeling you sometimes get, that little flicker of doubt where something just doesn't feel quite real? Well, we're about to dive headfirst into one of the most mind-bending questions ever asked, a question that blurs the line between science fiction, hard physics, and some really deep philosophy.
So let's just put it right out there. Is everything around you, the chair you're sitting in, the air you're breathing, your most cherished memories, is it all just incredibly complex lines of code? Could we be, right now, living inside a vast, sophisticated computer program? Now, I know it sounds like something straight out of a movie, but this is a serious possibility that scientists and philosophers are genuinely wrestling with.
And you might think, okay, this is a pretty new idea, born from our obsession with computers and video games, but here's the thing, it's not. This question is ancient. I mean, long before anyone even conceived of a computer, philosophers were asking a disturbingly similar question: is the reality we see really reality?
Yeah, check this out. On one hand, you've got ancient thinkers. You've got Plato, who imagined us as prisoners in a cave, mistaking shadows on a wall for the real world. You have Buddhist philosophy suggesting that everything we experience is just a creation of our own mind. Now fast forward to today. The modern hypothesis takes that same core doubt and gives it a high-tech twist. It says, it's not a shadow, it's not a mental projection, it's a literal computer simulation.
This is what's known as the simulation hypothesis, and it was really put on the map by the philosopher Nick Bostrom. His argument is actually pretty straightforward, but wow, is it powerful. Think about it like this. If any civilization, anywhere, ever, gets advanced enough to create super realistic simulations, say to study their own past, they probably wouldn't run just one, right? They'd run thousands, maybe millions of them. So if that's the case, what are the odds? Are we in the one single original base reality, or are we in one of the countless simulated ones? Statistically speaking, it's way more likely we're living inside the code. So why do so many people find this idea so compelling? Well, it's because when you start to really look at the universe, proponents of this theory say you can find some strange, almost code-like features. It's like we can spot potential glitches in the matrix. The similarities are kind of spooky, aren't they? Our universe runs on these unwavering laws of physics, just like a computer program has to follow its core rule set. We've got a universal speed limit, the speed of light, which feels an awful lot like a processor hitting its max clock speed. And maybe the weirdest of all, at the tiniest, most fundamental level, space itself seems to be pixelated at a scale called the Planck length, just like the screen you're looking at is made of pixels.
Let's just hang on that speed limit for a second. We know from Einstein that nothing with mass can reach the speed of light because it would take an infinite amount of energy. Now, doesn't that sound a little arbitrary? It doesn't sound like a natural feature of reality so much as it sounds like a hard-coded limitation in a system, a rule that just says, nope, you can't go any faster than this, period.
And then you get to the absolute weirdness of quantum mechanics. Okay, so a particle, like an electron, doesn't actually have a specific location until you observe it. It's just a cloud of possibilities. And this is startlingly similar to how a video game engine saves on processing power. It doesn't bother rendering all the detail in the world behind your back, it only draws it when you turn to look at it. So why would the universe waste resources defining a reality that nobody's even looking at? It's an incredibly powerful and honestly a very seductive analogy.
Okay, so the analogies are cool, they're compelling, but for every one of them, there's a problem. A really, really big one. Because when we stop talking philosophy and start looking at the cold, hard numbers of physics, the whole simulation idea slams into a gigantic wall. And it all boils down to this fundamental concept in physics known as Landauer's principle. And what it says is that information isn't just an abstract idea, it's physical. Every single time a computer performs a calculation, every time a bit flips from a 0 to a 1, it generates a tiny, unavoidable amount of heat. So, computation has a real physical cost. It takes energy. And when physicists actually sit down and calculate the energy cost to simulate our universe, well, the numbers just get ridiculous. This number you're looking at right now, that is the absolute minimum amount of energy you would need just to store the information to describe our universe. We're not even talking about running the program yet. This is just the energy to hold the data. It's a number so huge, it's practically meaningless.
Until, that is, you put it in context. The energy you need just to store the data for the simulation is far, far more than all the energy that actually exists in our entire observable universe. That's every star, every galaxy, all the matter, all the dark energy, all of it combined. The conclusion here is pretty stark. Our universe physically does not have enough energy to simulate itself. It's just not possible.
Aha, you might say, but what if the simulators are just being clever? What if they're not simulating the whole universe, but just our little corner of it? Just Earth, and the stars are like a fancy background image, a skybox from a video game. Well, even if we make that massive short count, the energy needed just to store the information for planet Earth alone is still this absolutely astronomical number.
To get your hands on that much energy, you would need to take a globular cluster, that's a dense ball of hundreds of thousands of stars, and convert its entire mass perfectly into pure energy. And remember, that's not to run the simulation day to day, that's just to boot up the program.
So according to the laws of physics as we understand them, a full-scale simulation of our universe, or even just our planet, it's physically impossible. That's the direct, blunt conclusion from astrophysicist Dr. Franco Vazza, who actually ran these calculations.
But the problems for the simulation hypothesis don't just stop with physics. Even if somehow you could conjure up all that impossible energy, you'd immediately run into another, maybe even more fundamental roadblock. A wall built not of energy, but of pure, unbreakable logic.
So there are these three monumental theorems in mathematics, from geniuses named Gödel, Tarski, and Chaitin, and they all point to the same profound conclusion. They prove that any system that's based on a finite set of rules, which is exactly what a computer program is, has certain limitations baked right into its very structure. There will always be true statements it can't prove, complexities it can't create, and questions about itself it can never, ever answer.
So what does all that complex math really mean for us? It means that a computer program, I don't care how powerful or complex it is a closed, finite system. And these laws of logic prove that any system like that is, by its very definition, incomplete. It can never contain the whole truth about itself.
And this right here gets us to the absolute core of the logical problem. If our reality contains things that just can't be boiled down to an algorithm, things like genuine, unpredictable randomness, or maybe the biggest mystery of all, consciousness itself, then a finite computer program is mathematically incapable of ever fully capturing it. This isn't an issue of not having enough processing power. It's a hard limit of logic itself.
So physics says it's impossible. Mathematics says it's impossible. Case closed, game over, right? Well, maybe not, because it's possible we've been asking the wrong question this whole time.
What if we stop thinking about this as a literal fact and start thinking about it as a powerful metaphor? Yeah, the idea that we are literally characters inside a giant cosmic computer seems to be ruled out. But what about the idea that our universe runs on rules that behave like a computer program? Now that turns out to be an incredibly useful way to think about some of the deepest, weirdest puzzles in physics.
And this is where the physics paper we've been talking about drops one last absolutely stunning plot twist. The scientists conclude that a universe with our laws of physics can't simulate itself, but they leave the door open for a wild possibility. What if our universe is being simulated by a computer in a completely different universe? One that operates under totally different physical laws, where maybe energy is way easier to come by, or the rules of computation itself are just different.
And this is where using the simulation as a metaphor becomes so powerful. Take quantum entanglement, what Einstein famously called spooky action at a distance. You can have two particles linked across the entire universe, and when you measure one, the other one instantly changes, faster than light can travel between them. How is that possible? Well, if you think of the universe like a computer network, the answer is surprisingly simple. The particles aren't sending a signal to each other. They're more like two computer clients referencing the exact same file on a central server. When you update the file on the server, both clients instantly reflect that change. There's no signal, just an update to a single underlying piece of data.
And so, this is the profound and beautiful mystery we're left with. The evidence seems pretty clear that we're probably not living in a literal computer simulation. And yet, the deeper we look into the fabric of reality, from the cosmic speed limit to the strange logic of the quantum world, the more it seems to be built on information, on rules, on something that looks an awful lot like code. So the final question really is this: if our universe isn't a simulation, then why on earth does it look so much like one? That's the mystery that's waiting for us to figure out.